assistant.
Okay, so here we go.
Yeah.
Hi class, this is the review for the second exam, and the first important message here is do not watch this, because math is not a spectator sport. Namely, if you're watching this, then you're not going to learn the stuff. So first and foremost, do the problems yourself, then you can watch this. So please turn this off now so you don't see this, okay? Turn it off, don't watch, go do something else. Well, go do the review problems. For you, they're still there. Now we start reviewing here. First problem, error count codes. Show there's no code with 4 information bits and 2 extra bits. That's a total of 6 bits. They can create 1 error. Well, if there was a such code, so let me write 1 here, first problem. Okay. If there was such a code, I'm writing too much, then there'd be 2 to the 4 code words. And then, if you think in the whole scheme of things, around each code word, you get lying here in the space. This is a total of 6 bits. Look at the board like this. Aha! How size is big this size? Well, this is going to have 1 code word, and then there's 6 code words on distance 1 from it. Having distance 1. Aha! And that means that you have 16 for the code words, 1 for the code word, and then 6 for all the neighbors. And we calculate this out. Notice that this is, wait a moment, this is, what is this? 16 times 7, that's bigger than 16 times 4, which is 2 to the 6. And since the code will have length 6, there can't be such a code because we get this inequality here. i.e., with 6 bits, you can't determine 16 times 7 choices. Okay? Let's do part B here. Well, now, in the second thing, if we code of length, so notice this had length 6 on this one. In this one, the code would have length. You can probably read my handwriting anyway, so why I'm writing for, I don't know. Length here would be 7 plus 6 is equal to 13. 7 information bits, that means 2 to the 7 code words. But now, notice that can we correct 2 bits? That means if you have a code word, not only it's a sphere, it's a sphere, ball, radius 2 around here. So notice that is 1 code word. There are 13 things here on distance 1. And the 13 choose 2 things that can be further away here on distance 2. So remember this 13 times 12 divided by 2, whatever this is. Remember, you can choose the first bit in error in 13 ways. You can choose the second bit in errors in 12 ways, but order doesn't matter. I divide by 2. So this is 13 times 6. 13 times 6 is what? 78 on distance 2. So now you note, aha, tra-la-la. Now you note that 1 plus 13 plus 78, well, this is the beginning of a row in Pascal's triangle, times the number of code words we have, it was 2 to the 7. This thing, let's calculate this. No, this is hard. 13 plus 78 is what? Can't add. 91. This is 92 times 2 to the 7. which is bigger than 64 times 2 to the 7, which is 2 to the 6 times 2 to the 7, which is 2 to the 13. So we only get the 13 bits coming in. However, with this 13 bits of information, we cannot distinguish between this many possibilities, hence there's no such code. No such code. Ta-da! Let's now go to problem number 2. Aha! Problem number 2, we're using this matrix to construct the code, and the code words are the null space of this matrix, and we get this vector R here, 1 0 1 0 1 0 0 1. So what we have to do is to multiply problem 2. We have to multiply the matrix. Let me do this. Let me write that. Shall I write out the matrix for us here? Here's the matrix. So we have it. 1 0 0 0 1 1 0 0. This is going to be really boring. I just make sure I get the right matrix down. Okay. The top row are all equal to 1s. Okay, I should have thought a little better when I was doing this, but here's the matrix. And now, this matrix times the first vector, that vector over here. The first vector was 1 0 1 0 1 0 0 1, and multiply. Okay. First addition, matrix multiplication goes this way, so I just add up 1 plus 1 plus 1 plus 1. Remember, everything is mod 2. I love mod 2. Good is equal to bad, plus is equal to minus. Next one we're doing, here I get 0, 0, 0, and 1. Then we get the next thing here, 1, 0, and put down the 0 here. And finally I'm adding the last thing, 0. So note that the vector we get, this is not a column vector. Hence, there were at least 2 errors. Remember, this is the code where we can correct 1 error, but only detect 2 errors. So the many possible errors, 2 errors are going to happen here. Okay, that was the first thing. Now let's do the second vector we have to decode. So now I can multiply this matrix with the vector 0 1 0 1 0 0 1 0 0 0 1 0. Okay, here we go. First thing here, you just add everything up. That gives you 1. Next thing you're going to add up 1 plus 1 plus 0 plus 0. That's a 0. Next thing you add up 0 plus 1 plus 0 plus 1. That's a 0. And then the last 4 bits, you get 1 here. Okay, and now if you look at the matrix, you realize that this is that thing. This is the 5th column vector. So error in the 5th bit, i.e. 5th bit is here. So the vector that was sent was 0 1 0 1, then 1 0, 1, 0. This was a cool thing, the vector was sent. Ta-da, that was problem number 2. Now we go on to matrix multiplication. Ta-da-da! Maybe I should fit the paper on the screen here. But the first thing, third problem, x cubed, well it's really, no, I can't write, 2x squared plus 0x plus 2 times x to the 4 plus 0x3 plus 2, no, plus x squared. I'm sorry, I can't even read my own notes. Okay, so that means we had a 1, 0, 1, 2, 2. That thing. Now I think I'm confusing myself. Let me stop confusing myself. Okay, so I have to multiply this thing by 2. That is 2, 0, 2, 1, 1. That multiplication with that thing. Multiply by 0, I don't have to do. Multiplication by 2 again. Shifting it by 2 steps to 1, 1, 2, 0, 2. Then multiplying by 1, the x cubed. That means I get 2, 2, 1, 0, 1. Add. Remember, everything is happening in mod 3. I should have said that earlier for this problem. Sorry about that. 1, 1, 0, 0, 0, 1, 2, 1. So this is going to be what? X to the 7, 2x to the 6 plus x to the 5 plus 0, 0, 0 plus x plus 1. Pam, pam, pam. Now let's go on to the next one. The next one, part B here, takes place in integers modulus 2, those polynomials, and I can compute x plus 1 to the 18. Now, wait a moment. Let's be smart. Namely, this is x plus 1 to the 16 times x plus 1 squared. And now, since the coefficient happens modulus 2, each factor of 2 in here, that's just going to jump in. So the first step, you notice, is just x squared plus 1 to the power of 8. This jumps in also. This is just x squared plus 1 over here. And then you know the next jump factor in. This is really boring, as in I'm being too pedantic. You should probably stop and fast forward now. Okay, but I can't fast forward the thing. Camera at the moment is boring. Okay, so remember, this is the freshman dream that you can use, take powers 2, mod 2, you can take powers 2 and just put them in. And now we can just multiply this thing out. It's x to the 18 plus x to the 16 plus x squared plus 1. Well then, nice and easy and quick. And in fact, when you do this, you can even you can skip all the middle steps here, and you can jump. You can jump from here directly to here. So that's what you do. Okay. Now you realize that part C is really fun also here. Now this takes part in integers modulus 3 x plus 1 to 27. Aha, 27, you know that's 3 cubed, so let's use powers of 3. So this is just x to the 27 plus 1. Done. Done. Okay, next thing. Haha, division. Number 4. Okay. And the most important thing to point out, this is happening in mod 3 on the coefficients. Okay, so the polynomial I'm dividing with is 2x cubed, 1x squared, no linear term, and constant term 2. and dividing into x to the 7, 2x to the 6, no x to the 5, and x to the no, that's a 1. Sorry, 1x to the 4, 1x cubed, 1, 2, x squared, no linear term and constant term. Okay, so 1, 2, 0, 1, 1, 2, 0, 1. Okay, first of all, 2 goes 2 times in 1. Multiply here, multiply this 2, 2, 2, I get 1, 2, 0, 1. My goodness, is that what's happening here? I guess it is. Am I crazy? Yes, it is. I get 0 here. Then there's no need to multiply by x. I can bring in 1 here, I can bring the 2 down, I can bring the 0 down, 1, and 0, 0, 0, and it's 2 here. Again, subtract off 1, 2, 0, 1, and get 0. So the quotient is 2x to the 4 plus 2, and the remainder is 0. That was strange. You mean I have to write a problem that was that nice? That's not possible. I'm not that nice. Haha! Problem number 5. And number 5 is Beesut, our hero. Okay, so we now going to Beesut here. So what are the polynomials? Well, let's not write them out. 0, 0, 1 is the matrix. The first polynomial is x to the 4, 2x cubed, 1x squared, no linear term, and it's constant 2. That's the first polynomial. The second polynomial is 1x to the 4, no x cubed, a square term, one linear term, and 2 is a constant. Okay? Well, clearly I want to use that one to kill off that one. So just add 2 to multiply the load. And notice, the things takes place here. Coefficients are modulo 3. Okay? That's important. If you don't know where it takes place, then you don't know what's happening. So, okay. 1 times 2 is 2 plus 1 is 0. Don't write them. 0 times 2 is 0 plus 6. I get 2 here. 2 times 2 is 1 plus 1 is 2. 1 times 2 is 2. We get a 2 again here. And 2 times 2 is 1 plus 1 is 0. So we get 1. Okay, now we want to use this 2 to kill off that 1. Well, you can use add, so plus x. Remember, x is shifting. Remember, shifting means the action is going to go this way. Okay. So here we go. 1, 2. Okay. I can write top row out first. Well, 2 plus 1 is 0. 2 plus 0 is 2. 2 plus 2 is 1, 0 plus 1 is 1, and the 2 just remains. Well, I forgot it over here. 1 plus 1 gives 1, 0, and here I get 2, 1. Now, if you look at this thing, we actually have a choice. Either I can multiply the top row by 2 and add it here, or I can multiply the bottom row by 2 and add it here. But let's just have the action continue from the top row acting upon the bottom row. So here we go. 1, 2, 2, 2, 2, 0. Then now there's no shift, there's no x here, so it goes straight down times 2, so 10. It becomes 12. Well, not 12. X plus 2, but it's funny to say 12 and x plus 2. 2 times 2 is 1 plus here, blah, 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 1. Okay. I hope I'm doing everything correctly here. And unfortunately, you're not here, so you can't correct me. So here we go. It's like sitting in prison, no one to talk to. 2 times 2 is 1%, that's 0. 2 times 2 is 1, that gives 2 here. 2 times 2 is 1, that gives also 2 here. And doesn't change that to, aha! Do you notice what happened this time around? I got that. Now you see in the next step, if I subtract here, I add this, multiply this by 2 and get here, you see this is the same thing. So this is stop. So, aha! Stop. So what do we know? We know then that this polynomial, 12, is x plus 2. X plus 2 times my first polynomial, that was called a of x, plus this polynomial, 2x plus 2, times my second polynomial, we call v of x, we get that's equal to 2x squared plus 2x plus 2, or I can multiply this thing by 2 to look past q by 2x plus 1 times a of x plus x plus 1 times b of x equal to x squared plus x plus 1. Especially the GCD of these two polynomials, a of x and b of x, is, well, either you can say 2x squared plus 2x plus 2, or x squared plus x plus 1. Because remember, GCDs are not, is only defined up to scalar multiple. So that was problem number 5. Now let's get on to problem 6. Problem 6, the least common multiple. Aha. Well, since I just asking for least common multiple, I can do Bezout on it here, but I don't have to keep the coefficient matrix, the identity matrix we started with. So I can just write down what these polynomials are, but the matrix, and I skip the first thing. So 1. Wait a moment. Important to note that this thing is happening in integrals modulus 5. Okay, remember that now. 1, 3, 3, 2, and 1, 0, 0, 4. So the Bezouting, I will write things over here, but I don't care about that. I'm only interested in computing the GCD and then the least common multiple. So here we go. Plus 4. That we kill off using this one to kill off here. Remember, mod 5 plus 4 is same as subtracting, so I'm going to get nothing here. That 3 remains, that 3 remains. And now 2 minus 4 is what? 3. Yeah, I'm going to say this. 4, this is 16 plus 2 is 18, 18 mod 5 is 3, yeah. 1, 0, 0, 4. Now, how can I kill off this one? Well, 3 times 3 is 9, which is 4, and I got it here. So plus 3x. Remember the diagonal action, now we shift here. We shift, and what happens? I get 3, 3, 3 here. That 3 is 4 to cancel that. That's 3 times 3. That can be 4. Then 3 gives also 4 here, and this 4 remains. If you now look at this thing, of course, you realize that GCD, these are your scalar multiple from each other, so the answer to GCD is, and let's just write this as x squared plus x plus 1. I mean, I can divide by 3, I can divide by 4, okay? Aha! My GCD is this, but that's not the GCD I wanted. I wanted the least common multiple. So let's take the fact these polynomials. Well, if you look at it, So if you can just look at it, well, let's do polynomial division perhaps. 1, 1, 1 divided into my first polynomial, 1, 3, 3, 2. 1, 3, 3, 2. And multiply by 1, 1, 1. I subtract 2, 2. This 2 comes down. I put a 2 here. 2, 2, 2, 0. So my first polynomial factors as well. Let's write the polynomial so we actually can see it. Factors is x squared plus x plus 1 times x plus 2. Then the second polynomial, we will divide now 1, 1, 1 into x to the 4, no x squared, no linear term here. Okay, this is 1 I should put here. 1, 1, 1, subtract 4, 4, that 4 falls down. I should multiply by 1 times 4 to kill off this thing. So 4 here, 4, 4, 4, subtract 0. Aha! So my second polynomial, x cubed plus 4, factors as x squared plus x plus 1 times x plus 4. So now, to summarize, the least common factor hence is the product of the two polynomials first one is the second one divided by the GCD x squared plus x plus 1. So what is this equal to? I can cancel a factor here, ta-da-da. So we are left with x plus 2 times x plus 4 times x squared plus x plus 1. Okay, let's just for fun multiply this thing out. What's this thing? This is easy to do directly. This is x squared plus, and linear term I just had to add the two things. It gives me x, 2 times 4 plus 3 times x squared plus x plus 1. I can multiply this thing out. 1, 1, 3, 1, 1, 3, 1, 1, 3. Just shifting. 3, 4, 0, 2, 1. We get the least common multiple x to the 4, 2x cubed plus 4x plus 3. Oh my goodness, I did this correctly. At least I know I did the same things last year. Ha! Whenever I did this. Now, problem 7. Factoring. Oh my goodness. Factoring is a pain in the butt. But here we go. It's kind of like, it's like medicine. It tastes bad, but it's good for you, okay? Okay, first polynomial out to be factored here. Problem 7 is x to the 4 plus x cubed plus 4x squared plus 1. Let's call this something. P of x, have a name for it. And this lives inside polynomials with coefficients modulus 5. So first let's look for linear factor. i.e., are there any roots? Okay, that's true. P of 0 is equal to 1, so 0 is not the root. What's P of 1 equal to? Well, I get 1 plus 1 plus 4 plus 1. 4 plus 1, 5, this is 2, which is not 0. So 1 is not the root. Let's do the next easy one to do. That's actually P of 4, but remember 4 is equals minus 1. That makes it easy to do now. It means I get 1 minus 1 plus 4 plus 1. This is equal to 0. 4 is a root. Aha! Or rather, minus 1 is a root. So that means I can take this p of x, I can divide it. So minus 1 root, the same thing as x plus 1 is a factor. Okay, then let's divide it up. 1, 1, dividing into here. Okay, 1, 1, 4, 0, 1. Okay, 1 here, subtract 1, 1, I get 0. Then I bring down to 4, 0 here. You can see that I bring it down to 4 here. 4, 4, subtract, I get 1. Remember, 0 minus 4 is 1, 1, 5. Bring down that 1, the 1 here, 1, 1, and the remainder 0. That's a tiny 0. You can probably not see it on the camera, okay? It's not the camera's fault. It's my fault. Blame me. But you can't read my handwriting anyway, so what are we talking about this thing anyway? So now I know that my p of x factors as x plus 1 times x cubed plus 4x plus 1. Remember, that's x cubed plus 4x plus 1 was coming there. Aha! And now we just check this polynomial. Let's call this one something. Let's call that cube of x. Very imaginative, okay? Just go down the alphabet. Okay, so let's try. Does this have any roots? Well, let's see. Cube of 0 is 1. Not a root. Cube 1. I get 1 plus 4 plus 1. This is 1. Not a root. Let's try cube of 4 again. What is cube minus 1? I get minus 1 minus 4 plus 1. This is 1. Not a root. Okay, not be more adventurous. Let's try cube of 2. Cube of 2, I'm going to get 8 plus another 8. 4 times 2 is 8 plus 1. This is 17. This is 2. That's not 0, not 5. Finally, let's figure out cube of 3. But to make the number small, remember that 3 is the same thing as negative 2. What do we get? I get minus 8. Remember, this is minus 2 cubed. And then plus 4 times minus 2, another minus 8, and then plus 1. This is minus 15, which is 0. Aha! 3 is a root, or minus 2 is a root. So x plus 2 is a factor. So that means I can divide my q of x here by x plus 2. 1, 2, 0, 4, 1. Goes 1 time here, divide, I get 3, bring down that 4 down here, and then multiply by 3. 3 times 1 is 3, 3 times 2 is 1, subtract, I get 3, bring down that 1, multiply by 3 again, I get 3, 1, good. So g of x is x plus 2, is that x plus 2, times x squared plus 3x plus 3, equal to r of x. Does r have a root factor? Well, we can easily check that. R of 0 is 3, r of 1 is 7, which is 2, r of negative 1 is 1 minus 3 plus 3 is 1, different from 0. Then we have r of 2, get 4 plus 6 plus 3, 13, which is 3, is non-zero. And then r of negative 2, i.e. r of 3, I get 4 minus 6 plus 3 1, so no root. And since it has degree 2, it hence is irreducible. So you get that a big polynomial P of x, it was the first factor we found, then we found the factor x plus 2, and then we found the quadratic factor here, x squared plus 3x plus 3. Okay, now keep factoring. Oh, the next one is my example, and I remember doing this in class, namely x to the 4 plus 1. And so let me do it quickly, but change the order. Let's first look in the complex numbers. Well, complex numbers, if you solve the equation x to the 4 minus 1, you can get 4 roots here. So in the complex numbers, this factors at x minus 1 over square root of 2 minus I square root of 2 times that root, giving this factor. Then we do this one, x plus 1 over square root of 2 minus I over square root of 2. You should have this in your class notes, that in the factor. Then we get x plus 1 over square root of 2 plus I over square root of 2. Is that root. And finally, we do this one, x minus 1 over square root of 2 plus I over square root of 2. Okay, so over the complex numbers, you see that this factors all into linear terms. Now, if I go over to here, the reals, you have to now combine the complex conjugate roots. It means I'm going to combine that one and that one, and multiply this together. Then I get something like x squared minus square root of 2x plus 1, I think so. And combine these two, multiply them out. I think I get x squared plus square root of 2x plus 1. And if you so this is factorization of the reals, and then of the of the rationals. Notice that this is not rational polynomials, so the rationals you use factors x to the 4 plus 1. Okay, I did this in class. It's a good example. So it really shows you that where you're living, i.e. which field you're working with, really changing the factoring here. Here's 4 linear terms, 2 quadratic, and here just quartic, degree 4. Okay. Now let's take the same polynomial again, namely, but this time around do it over the field with 2 elements. The field with 2 elements is my favorite field, you know that. And same polynomial x to the 4 plus 1. Now, but this is obviously factors even more. If you just think for a moment, you realize it's just factors as that. Well, you know how to calculate this way, it gives that way, so there you are. Aha! But let's continue. X to the 5 plus x plus 1. And I'm doing the field of 2 elements. Yeah, I mean linear factors here. Well, no, because 0 is not the root. And P1, 1 plus 1 plus 1 is just 1, 0. So, no root, no linear factor. Then we have to check, degree 5, we have to check, is there a quadratic factor? And the only quadratic polynomial of degree 2 here is x squared plus x plus 1. So we can check this x squared plus x plus 1 factor. Okay, let's do the division. 5, 4, 3, 2, 1, 1. Take 1 here, 1, 1, 1. I subtract, I get 1, 1. This here comes down. I do 1 here, 1, 1, 1. I subtract again. I get 1 here, 1, 1 falls down, 1, 1, 1. Yes! So you notice here, I did get a factor in here x squared plus x plus 1 times x cubed plus x squared plus 1. So factors, and now look at this one. This one we know this is an irreducible polynomial of degree 3. So it has irreducible degree factor of 2, irreducible factor of 3. Okay. Now let's do the next one. Q of x equal to x to the 5 plus x squared plus 1. And we are still in the integrals modulus 2. I love mod 2. Yet again, you notice that q of 0 is equal to q of 1, which is 1, which is non-zero, so you have no linear factor. Now let's try the x squared plus x plus 1. 1. Okay, we do the division. And now just, wait a minute, let me split 1. We get the remainder 1 here. So x squared plus x plus 1 is not a factor. But now, there's no need to go on to check the irreducible factors degree 3 here, because if you can factor something of degree 5, one of the factors has degree 3 or 4, and the other factor has to be degree 1 or 2, but there's no degree 5 factor. Hence, x to the 5 plus x squared plus 1 is irreducible. And we are done. There's no factoring happening. Okay, let's go on. Now, problem 8. I hope we're making progress. Well, first problem here. If x to the 7 plus x plus 1 is irreducible, what can you say about x to the 7 plus x to the 6 plus 1? It's also irreducible. For matrix multiplication respects of turning things backwards, reading coefficients backwards. I mean, here we have coefficients 1, 0, 0, 0, 0, 1, 1, and here we have coefficients 1, 1, 0, 0, 0, 1. So x to the 7 plus x to the 6 plus 1 should also be irreducible. Aha, the 6 irreducible norms in Z2 of degree 5, find them. Well, we did find one of them, agree? In the previous exercise. We know that x to the 5 plus x squared plus 1 is irreducible from part 7. And the other thing was, in the previous one, we found out that this one was not irreducible. Not. So let's think for a moment. If I have polynomial r of x, notice that we want r of 0 to be 1, so that means that we coefficient 1 at the end, and we want r of 1 to be 1. So if you have odd number terms, did I remind you that everything is happening here in mod 2? Okay. So the only polynomials we can list here, we should list all polynomials here. So let me list what we can do. We have this one, which is not. This one, which is irreducible. Okay. Well, this one is reverse of this one. So this one is also irreducible. And then we have this one. What's the reverse of this one? This one is not irreducible, so whoop, there goes. The other thing with 3 terms, 4 terms, where 1 is root, so we have 5 terms. So we have here x to the 5 plus x cubed plus x squared plus x plus 1, x to the 5 plus x to the 4 plus x squared plus x plus 1, x to the 5 plus x to the 4 plus x cubed plus x plus 1, and x to the 5 plus x to the 4 plus x cubed plus x squared plus 1. So these four polynomials, they don't have 0 as a root, do not have 1 as a root, so there's no linear factors. And now, the only thing that remains would be that you can factor this as a degree 2 times degree 3, i.e. degree 2 irreducible times degree 3 irreducible. But there's only 1 of degree 2 is irreducible, only 2 of degree 3 is irreducible, and those multiplications have just been here. Remember, we did one is part 7, so hence all of these are irreducible. So here you have the 6 irreducible polynomials of degree 5. So you need these if you ever can construct a code of the field of 32 elements, but let's continue. Part 9. Congruences, modular polynomial. This is not too bad. What we have to do, we have to multiply x squared plus 2x plus 2 with 2x squared plus 1. Well, let's do it. 1, 2, 2, 2, 1, 1. We get 2, 1, 2, 2, 2. But you remember now, this was mod x cubed plus 2x plus 1. So we just have to divide by this thing and compute the remainder here. So 1, 0, 2, 1. And here we have to divide into this thing. Okay, it goes 1 goes 2 times 0, with 2 here multiplied 2 by 0, we get 2, 0, 1, 2, subtract 0, 1, 2 minus 1 is 1, 0. This 2 falls down, 1, 1, 0, 2, 1, subtract. Why are you watching this, by the way? You're not supposed to be watching this thing, you're supposed to be working on the reuse all alone instead of him. So we get the answer is then that's the remainder x squared plus x plus 1, and it's amazing this way I got previous years also. Aha! That was problem 9. This is kind of fun. No, it's not fun, it's kind of boring because I have to sit here and talk to myself. I'm actually surprised I haven't fallen asleep yet. Aha. Next thing, we're given the following polynomial. P of x is x cubed plus 2x plus 1, and it's living in here. Okay. Now it's a degree 3 polynomial. Does it have any factors, I wonder? I always want it directly. So notice that P of 0 is 1. P of 1 is 1 plus 2 plus 1 is 1, and P of 2, well, I'm not going to do P of 2 into P of minus 1. 2 is equal to minus 1. I get minus 1 minus 2 plus 1. Whatever that is, it's not 0. So, no roots, no linear factors. Aha! So hence P of x is irreducible. Aha! So hence you know that when I quote out by this thing, this is a field. The greatest things in sliced bread. In fact, this GF 27. Hi GF 27. That was part A. Now change over to part B. Part B. Giving q of x equal to x cubed plus x plus 2. x cubed plus x plus 2, and remember we're still living polynomial tree mod 3. And here we go. Could it be a root here? Let's try. Q 0 is 2, that's non-zero. Q1 is 1 plus 1 plus 2, which is 1, which is non-zero. And Q of negative 1, which is Q of 2, is minus 1 plus 2, which is 0. Aha! X plus 1 is a factor. So Qx not irreducible. So if I mod out the polynomial ring by this thing, then it's not a field. And that was problem 10. Damn! Oh, I shouldn't do that. The camera equipment might fall down on me. That wouldn't be nice. Now we go on to problem 11. We have to compute inverses of polynomials. You can do Bezout, and more Bezout. I love Bezout. Sorry about that, I forgot there was a joke coming up here, but do you ever see the movie Princess Bride? You should, okay? It's a good movie. Go and rent it somewhere. But first do the review sheet, then go and see Princess Bride, okay? Just in the right order. So I have two polynomials here. P of x equal to x cubed plus 2x plus 1, and a of x equal to x squared plus 1, and they're all living in the coefficients modulo 3. And I want to compute, is there an inverse to this polynomial, mod that polynomial. Okay, so we have to start Bezout 1, 0, 0, 1, boop. Here's P of x, 1, 0, 2, 1, and here's a of x. Okay, plus 2x. So we diagonal action. So we get 1. Here we get 20. Okay. 1 times 2, 1 times 2, here I get 1 here, I get 1 here, 1, 0, 1. Then we get, now I have to use this 1 to kill off here, so we can do 2x again. We're going down. 1 here. This gives me, this is 2x, not 2x, this is 4x squared, which is x squared. So I get 1, 0, 1 here. Okay, this one goes off here. 1 times 2 is 2, 2, 1. Well, let's just add one more going down. $21. I get 121. 1 plus 2 is 0, 1 plus 1 is 2. Let me just multiply this row by 2. If I do that, I'm done. So I know that x plus 2 times my p of x plus 2x squared plus x plus 2 times this is a of x is 1. That one is that one. Aha! So now that means if I take this coefficient as mod p of x, let's make it in here. Then this equation goes around, then we get that 2x squared plus x plus 2 times A of x is coming to 1, not p of x. Okay, here we go again. Next part, so 11 part B. Okay, now we're doing this thing. Qx. Still everything is happening mod 3 on the coefficients. You should be happy we're not doing mod mod 17 on the coefficients, okay? Mod 3 is much better. Okay, and now the one continuum is b of x, and b of x is x squared plus 2x. Okay, here we go. Bisut, our hero. Well, maybe that was too much to say. 1, 0, 1, 2, that's q of x. And b of x is 1, 2, 0. And here we continue, plus 2x. Now we choose either we can add this thing to this one or this one to that one. Clearly you can see we can add on here, but which one gives the answer quickest? I don't know. Oh no, let's go down. That's fine. 2 plus 2 is 1, 2 plus 1 is 0. So take the last row, multiply that by 2. Multiply that row, I get 2, 2, 1, 2, 0, 1, 1. So hence we have that 2x plus 2 times q of x plus x squared plus 2x times b of x is equal to 1. So mod q of x, actually, I'm wondering if I should check my answer here. I don't know what I'm checking. Which problem is it? 11. Ha! Seems good. So hence we know that x squared plus 2x times b of x is congruent to 1 mod q of x. One more thing to go here. So do you want to stare that longer? I don't want to stare this longer. I think we're done. Okay, now at the next one. We have the same, so this is like part C, q of x, x cubed plus x plus 2, and this time around, can we compute the inverse of x squared plus 2? Okay, so here we go again. Bisut. Happy French guy he was. Zero. 2 times 2 is 1 plus that gives you 2. 2. Now I'm doing 2, and I added this one to get out this one. X. Important to keep things in straight columns. You know exactly what's happening. 2 with the 0, 2, 2. You notice, you realize now that the GCD is not 1. The GCD is 2x plus 2, or if you want x plus 1, and hence there is no inverse to C of x mod q of x. So I want you to observe something here, that we know that x plus 1 is in fact a factor in here. Well, x plus 1, that says that minus 1 is a root, and you look here, you see the fact minus 1 is a root here. So you see that this thing is not irreducible. Q of x, not irreducible. Okay, so counting mod q of x is not a field. However, if you go back for a moment, and remember, we did actually compute something earlier mod the same polynomial in part B here. So sometimes when you have a ring, elements can have an inverse, and sometimes they do not. So first we had an inverse, and the second part C here, we had no inverse. And in read on writing, inverse. Can we actually see this? Inverse, as if no inverse. Aha. And that was problem 11. Now we are problem 12. Problem 12. Here we go. This is a computation inside the field of 8 elements. Da 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 da. So hopefully you have this little table somewhere. Ba da da dum, ba dum, ba dum. And you remember, we obtained the field with 8 elements by taking the field of 2 elements and putting in this root to alpha cubed plus alpha plus 1 equal to 0. And what are we trying to compute? Is 1 to the 6 plus alpha to the 7 plus alpha squared plus 1 to the power of 8 plus alpha squared plus alpha to the power of 9. But this is peanuts, that is 1, okay? Alpha to the 7, in the field of 7 elements, you know that this fact is 1. So there's no problem. Alpha squared plus 1, alpha squared plus 1, look at that's alpha to the 6 here, or alpha inverse. Not very alpha to the 6, so alpha to the 6 plus 8. Alpha squared plus alpha, aha, that's alpha to the 4. So we have alpha to the 4 to the power of 9. Da da da. Remember, everything is now alpha 6 times 8 is 48. Alpha 4 times 9 is 36. But notice now that 48 is congruent to 6, not 7. So this is alpha to the 6. And 36 is congruent to 1, not 7. So that is congruent to alpha. Alpha to the 6 plus alpha. But we can simplify the fact further. Alpha to the 6, put into a little table, root alpha squared plus 1 plus alpha. So this is alpha squared plus alpha plus 1. Or if you want, we can write it as alpha to the 5. So you notice that the computation is very quick and efficient. If you have this little table, you can change between writing things of power alpha and polynomials of alpha. So that was problem 12. Nice and convenient. Okay. Next thing is problem 13. Aha! Now, here is the error correcting code. 7 bits long, 4 information bits, 3 extra bits, and we're doing this with a field of 8 elements. So what are we getting? We have to remember m of x in this case is x cubed plus x plus 1, and we receive r of x to be x to the 6 plus x to the 5 plus x to the x squared plus 1. First thing is you compute r of alpha. Alpha to the 6, alpha to the 5, alpha to the square plus 1. Let's make a little table to add things up. So according to our table here, alpha to the 6 is 1, 0, 1. Alpha to the 5 is 1, 1, 1. Alpha squared is alpha squared, and 1 is 1. We add it up, you get 1, 1, 1. This is alpha to the 5, well, really, alpha squared plus alpha plus 1. This is alpha to the 5. Haha, error in the 5th bit. This is an alpha to the 5. Error in the 5th bit. So hence, the code word that was sent means that the bong that's out is x to the 6 plus x squared plus 1. Was that quick and nice and wonderful? Okay. Now, problem 14, and look at this here. Problem 14. Problem 14 is the error correcting code of the field of 16 elements. So we have 11 information, 4 extra bits. Can we decode one error here? And remember now, the polynomial we're using is x to the 4 plus x plus 1. And that's exactly the same thing we have here, over here, x to the 4 plus x plus 1. So here we go. We should decode r of x. Okay, this is a pain in the butt because everything gets so long now, okay? Maybe I shouldn't say expressions like that, by lecture. This can be captured forever and ever on YouTube, okay? My grandchildren will watch this thing and say, "What? Grandpa said that?" This is like the worst thing you can do to yourself is to YouTube yourself. Okay. Luckily, I'm not looking in the camera the whole time, okay? So the next thing we have to do is r of alpha. Okay, we get alpha to the 14, alpha to the 30, alpha to the 9, alpha to the 8, alpha to the 5, alpha to the 4, alpha will give you plus 1. Okay, so let me use the table to add this thing up. Okay, and the table looks like this. It looks slightly bigger for you because I've probably blown up when I tried to print it. Okay, so here we go. Okay, I try to fit everything. I'm not going to fit everything on the screen here, okay? So here we go, r of alpha, we're computing. Okay, 14, 1, 0, 0, 1, 13, 1, 1, 0, 1, 9, 1, 0, 1, 0, 8, 0, 1, 0, 8, 5, 0, 1, 1, 0, 4, 0, 0, 1, 1, alpha cubed, and then 1. Let's add this up. 1 plus 1 plus 1 plus 1 is 4, 0. 1 plus 1 plus 1 is 1. I think it's 1, 2. I love 1, 2. You can love it also. 1. 1 plus 1 plus 1 plus 1 plus 1 is another 1. This is alpha squared plus alpha plus 1. Now we go back and we look at the magic table. Ha! It's alpha to the 10. So error 10th bit. So I guess the code word that was sent was c to the x equal to x to the 14 plus x to the 13 plus x to the 10, that one is corrected, plus x to the 9 plus x to the 8 plus x to the 5 plus x to the 4 plus x cubed plus 1. That's all the 15 bits, okay. But if you actually read the thing carefully, okay, it says here, it says decode. So. Okay, 14. Now for the last problem. Bum, 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 bum. Now it gets exciting. Problem 15. This is now the error correcting code that can correct 2 errors. Ha! So we had to calculate things here, so now we have to really calculate things. So part A, r of x equal to x to the 14, x to the 11, x to the 7, x to the 6, x to the 5, x to the 4, x squared plus 1. Okay, so first we want to calculate this r of alpha, and I'm just going to directly skip over, not write things out, because otherwise it's going to take too much ink. So, yet again, the table. Alpha to 14, 1, 0, 0, 1. Alpha to 11, 1, 1, 1, 0. Alpha to the 7, 1, 0, 1, 1. Alpha to the 6, 1, 1, 0, 0. That was alpha to the 6, alpha to the 5, 0, 1, 1, 0. Alpha to the 4, 0, 0, 1, 1. And then we get alpha squared. And then we get constant 1. Okay, now we add this thing up. 1 plus 1 plus 1 is 0. 1 plus 1 plus 1 plus 1, 0. As having happening about 2. 1 plus 1 plus 1 plus 1, 0. 1 plus 1 plus 1 plus 1, 0. So r of alpha is 0. Okay, don't give up hope yet. We have to compute r of alpha cubed also. So that means now we have to be careful. This is alpha to the 42. 14 times 3 is 42. Plus alpha to the 33. Plus alpha to the 21. Plus alpha to the 18. Plus alpha to the 15. Plus alpha to the 12. Plus alpha to the 6. Plus 1. And now, notice we can do everything now. Alpha to the 15 is 1, so we can do not 15 here. So this is really alpha to the 12. This is really alpha to the cubed, alpha cubed. This is alpha to the 6. This is alpha cubed. This is a 1. This is an alpha 12. Alpha 6 plus 1. So let's collect things together. I have 2 alpha 12. They're gone. Then I have an alpha to the 6 and alpha to the 6 here. They're gone. I can cancel that. Cancels with that. Alpha to the 6. Cancel with alpha to 6. The alpha cubes cancel the 1. Cancel the 1. Cancel. I get 0. Aha! So remember now. We get. Remember a magic polynomial. R of alpha x squared plus r of alpha squared x plus r of alpha cubed plus r of alpha cubed inside here comes out to be 0, so there's no error. that was part A, no error. Okay, now it's getting more exciting because we can't have this again. Okay, part 15, part B. Okay, so wait. So no error, so the code word was in fact exactly what we set. Green, so there it is. Now we receive x to the 14 plus x to the 13 plus x to the 6 plus x to the 5 plus x cubed plus 1. The first thing you have to do is calculate R of alpha. Okay, so I'm going to make this little addition table to keep track of the coefficients. Okay, using the magic table. A man's best friend. Alpha to the 14, 1, 0, 0, 1. Alpha to the 13, 1, 1, 0, 1. Alpha to the 6, 1, 1, 0, 0. Alpha to the 5, 0, 1, 1, 0. Alpha cubed, 1, 0, 0, 0, and 1, 0, 0, 0, 1. We add it up. 0, we add it up. 1, 1, 1. So this is alpha squared plus alpha plus 1. We look in the table and we see that's alpha to the 10. So first important fact here is R of alpha is equal to alpha to the 10. Next, so let's not lose this piece of information. Next thing is we have to compute R of alpha cubed. Actually, if it doesn't shine through, maybe I should put two pieces of paper down here. R of alpha cubed is equal to alpha to the 42, alpha to the 39, alpha to the 18, alpha to the 15, alpha to the 9 plus 1. Powers of mod 15 is alpha to the 12, alpha to the 9, alpha to the 3 plus 1, alpha to the 9 plus 1. So this is, well, the 1's cancel, alpha 9 cancel. This left is really alpha to the 12 plus alpha cubed. And now if you do this addition, alpha to the 12, alpha cubed plus alpha squared plus alpha plus 1, which is 1, 1, 1, 1 plus alpha cubed, 1, 1, 1. This is alpha to the 10. Also, of course, alpha squared plus alpha plus 1. So we have R of alpha cubed equal to alpha to the 10. Okay, so let's now reference together what we know. So the polynomial, the equation we're going to solve I'm just writing that down at the moment. This is alpha to the 10 times x squared plus alpha to the 20 times x plus alpha to the 30 plus R of alpha cubed plus alpha to the 10. Well, I want to divide by alpha to the 10 to make this, to get the leading coefficient to be 1. So divide by alpha to the 10 is, dividing by alpha to the 10 is the same thing I'm multiplying to alpha to the 5. So I'm looking at this equation, x squared plus alpha to the 10 times x plus alpha to the 20 plus 1 Let me rewrite this in better form. X squared plus, what this is, alpha squared plus alpha plus 1 times x. Alpha 20 is alpha to the 5. Okay. Alpha to the 5 is alpha squared plus alpha. So this is plus that thing. It's funny, the same here and same here, but don't confuse it. Just let me write it out. Times x plus alpha to the 10. So remember, I want to solve this equation. It's going to have two roots, alpha to the I times alpha to the j. So what do I want? If you just multiply this thing out, you're going to get an x squared, you get alpha I plus alpha j equal that thing. So let me just multiply it out of here. Everyone to see. So what we need, alpha to I plus alpha to the j equal to, the linear term should be this thing, alpha squared plus alpha plus 1. And I need, the other thing is, I need I plus j to be congruent to 10 mod 15. Right? That's what we need. So now we have to solve this thing, and here we go. So I j is alpha I plus alpha j. I and j is going to sum to 10. So 10, 5 plus 5, we go on 10 same root. So that's 6, 4. And then let's increase I by 1 and decrease by 1. So that's 6, 4. We can have 7, 3. We can have 8, 2. We can have 9, 1. We can have 10, 0. We can have 11, 14. Remember, 0 minus 1 is 14 by 15. Then 11 plus 1 is 12, 12, 13. And remember, I wanted this to be alpha squared plus alpha plus 1. So I'm going to be a little bit tricky. I'm just going to look at the table, and if I load 6 and 4, alpha to 4 plus alpha to 6, that can begin with an alpha cubed plus other terms, which is not beginning like this thing. So it's not this thing. 7 cubed. Here we add alpha to the 7th alpha cubed. We get alpha plus 1. Well, that's not our target. So not in. Alpha to the 8 is alpha squared. Alpha to this 1. It's not that thing. Then we have alpha to the 9 plus alpha. That begins with alpha cubed, so it's not that thing. Alpha 10 plus alpha to the 0. The alpha 10 plus that is just alpha squared plus alpha. Now we have alpha to the 11, alpha to the 14. There we get alpha, new alpha cubed. We get alpha squared, we get alpha plus 1. Aha! You say that's what we're looking for. The roots are alpha to 11, alpha to the 14. So errors in 11th and 14th bit. Actually, you can check 12 and 13 here. If you add them, you get what? You get an alpha, so that's not that one. Okay. So tam tam ta da 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 da. 11th and 14th bit. Ta da 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 dum 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 da dum 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 dum. Dum 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 dum. So here was the code word we were sending. Da 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 da. So the corrected code word You just have to remove x to the 14, add in x to the 11. C of x equal to x to the 13, x to the 11, plus x to the 6, plus x to the 5, plus x cubed plus 1. Ta 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 ta. And now for the last of the last problems. Decode R of x here. So this is 15c. We receive R of x to be x to the 14 plus x to the 13 plus x to the 11 plus x to the 7 plus x cubed plus 1. Okay? So first we calculate R of alpha. I'm just going to make this directly. So make a little table. And we use our thing for the field of the field of 16 elements. So alpha to the 14, that's alpha cubed plus 1. Alpha to the 13, that's alpha cubed, alpha squared, no alpha plus 1. Alpha to 11, 1, 1, 1, 0. Alpha to the 7, 1, 0, 1, 1. Then alpha cubed, and then 1. We add it up. 1 plus 1 plus 1 plus 1 plus 1 is 5, but 1 plus 1, 2. 1 plus 1, 0. 1 plus 1, 0. 1 plus 1, 1 plus 1, 0. This is alpha cubed. Good. The next thing we need is R of alpha cubed. Okay, so substitute alpha cubed in R of x. We get alpha to the 42. 42 is 3 times 14. Alpha to the 39 plus alpha to the 33 plus alpha to the 21, and now alpha to the 9 plus 1. Remember now the powers are mod 15, so this is alpha to the 12, this is alpha to the 9, this is alpha to the 3, this is alpha to the 6, alpha to the 9 plus 1. The two alpha 9s cancel, so let's just write it out nicely. It's alpha to the 12 plus alpha to the 6 plus alpha cubed plus 1. Use the table to do this. Alpha 12 is alpha cubed plus alpha squared plus alpha plus 1. So we get 1, 1, 1, 1. Alpha to the 6, alpha cubed plus alpha squared. 1, 1, 0, 0. The alpha cubed doesn't outlet 3 there. The alpha to the 3 just alpha cubed itself, and 1. And we add that up, you get 1, 0, 1, 0. It's alpha cubed plus alpha. We look in the table, alpha cubed plus alpha is over here, that's alpha to the 9. Aha! So now for the grand finale, we need one piece of paper. So we have, we capture R of alpha is alpha cubed. R of alpha cubed is alpha to the 9. So now here's the magic polynomial we should calculate. R of alpha times x squared. R of alpha squared times x plus R of alpha cubed plus R of alpha cubed inside. We got alpha cubed times squared plus alpha to the 6 times x plus alpha cubed cubed is alpha to the 9 plus that one is an alpha to the 9. Notice alpha plus 9 by alpha plus 9. Now alpha to the power of 9 plus alpha 9, that cancels. Boom, boom. We left with this thing. So you see this new constant term. So while you can bring out an alpha cubed term, you can bring out an x. and left is x plus alpha cubed. Hooray! So that means you see root, well I should say non-zero root, is alpha cubed. So error in the third bit. So then if you go and look now, go that little bit. So the thing that was sent then was, so notice there's only one error, was then x to the 14 plus x to the 13 plus x to the 11 plus x to the 7. Now we switch that bit, so that plus 1. Ta-ta! And that was the end of the review sheet. And now, closing credit. Da-da-dum-dum, da-da-da, da-da-da-da, da-da-da-da-da, da-da-dim-dim, da-da-da, da-da-da-da-da, da-da-da-da-da-da, da-da-da-da, da-da-dum-dum, da-da-dum-dum-dum, bum-ba-dum-bum-bum.